Okay. Yes, so YouTube link is okay. Let me paste it here also. It is available now in calendar. Okay, so today is the first session for week 4, and it will be an open session. So I hope all of you gone through with the lecture at least. Is that true? All of you went at least once, have
Yes,
seen
sir.
this lectures.
Yes, sir.
Okay. So first thing is, anyone have any kind of doubt? Anyone?
Sir, mostly about eigenvalues and diagonalization.
Okay. Yes.
Orthogonal diagonalization.
Yes. We'll discuss today that. Even so, regression is,
Sir,
it
go
is.
with the summary, sir.
Yes. We'll try to do a summary. Okay. Any specific doubt? Anyone?
Sir, I have a doubt, but from week 3.
Okay. What is the doubt?
Uh, Sir, I am not able to differentiate between how a vector can represent a plane and a line.
Okay.
I mean, how to identify that? Whether a vector represents a line or a plane.
Okay. So a plane is generally you ask in 3D, right?
Yes,
In
sir.
3D. So if you are just, if you are, just a second, where it is. So it would be, if the algebraic expression is given for asking, once you see and then tell, is that represent a line or plane? Is that in algebraic, like some equations is given in that form you are asking?
Yes, sir.
So generally, if it is a kind of this one, it will be of, generally a plane would be represented like this. Okay, so that's that. Okay, x, y, z. Generally, the process is this represent point, and it would be a relation between all x, y, z. And if that plane is passing through origin, so it would be 0 here. Okay, and
Okay.
if it is not passing through origin, so it will be some constant here.
Okay.
Okay, so this will always be any kind of, let's say here, let me write in a more general, ax plus by plus cz is equal to t. Okay, where all a, b, c would be, t will be a coefficient, will be a real number.
Yes.
Okay, and if these things you are getting, this represent a plane, and for line, the line would be of this kind of x, y, z, but the relation would be in, it will be in a parametric form, like it would be of intersection of two planes. Okay, it would be represented by intersection of two planes. Okay, equal to z, sorry, equal to d, and another it would be a prime x plus b prime y plus uh, c prime z is equal to d prime, where all a, b, c, d will be a, so it would be a intersection of two plane. Either it will represent a line, generally we know if a plane intersect, okay, two planes will intersect, so they will intersect on
The line. Yes.
okay. And another way is it would be of this form: x is equal to y equal to, or maybe of this x is equal to some parametric notation would be, let's say alpha, y is equal to some alpha, sorry, beta, z is equal to, no, not this one, this is represent a point, okay, maybe of this kind of x is equal to y is equal to z, maybe here it would be alpha, beta, gamma. Of this kind of representation you will see,
Okay, sir. Got it.
okay, where alpha, beta, gamma would be of any real number.
Okay, sir.
So this generally would be, here it would be yeah, that's all.
Okay. Thank you, sir.
Okay. So in week 4, the contents are, regression. That is, simple
Linear, sir.
regression, a simple, that is, already a tutorial is there. I think everyone got clear with that concept, how it is working. It is exactly, if you change that in a 2D, then it will be a least square method. Otherwise, be a regression, you can think. Then polynomial regression is there. And then after we'll move to in week 3 we studied only I think it was generally differentiability continuity limit was there, I think so. In week 3 it was I don't know, it was okay for fundamental of projections also there. Okay. And then eigenvalues and eigenvectors are there. Eigenvalues, eigenvectors, and then diagonalization is there, and then orthogonal diagonalization. Okay. So regression is, it is just, least square method, same formula is there, same everything is there.
In
Polynomial.
week 1 also, no, sir. Linear regression.
Sorry, week 1.
Linear regression is also in the week 1, na?
Week
Start.
1. So even we can skip this part. Let's start from this eigenvalues, eigenvector, diagonalization, and orthogonal.
Sir, polynomial regression is important.
So yeah, polynomial regression is there, and all actually these all just formula. Even understanding behind the concept, that's fine, but it is just a formula. We'll just follow those only. Polynomial regression is there. What is that? We have some data points, and so what is the regression? We know, right? We have some data points, collection of some data point, and will regression means to try to get a proper best fit line. That's the meaning here. But what is the polynomial regression is that if these data are there, so we'll try to get a polynomial, okay, which will connect the all points. So we know, right? A polynomial is a smooth kind of function. Polynomials are nothing but a function which is of this form. Here, here a general form is saying to be a, or let's say a1, a2, x plus a3, a1 next one. And let's say this is a0, a1, a2 square, then a cube, sorry, a3 x cube. So this will be go till how many degree, till which degree we want the polynomial, we can do this. So till x to the power n. So polynomials are nothing but a function which we have already studied in maths 1 more in more detailed form. So what is in the regression is that we are try to get a proper or best fit, not line. Here is best fit polynomial, which will connect all points, and what is going to be the proper polynomial. And to get that polynomial, this is the thing here. This is the formula. That A is our whatever the matrix we get from the data, and this theta we want. Theta is theta 1, theta 2, theta 3. What is here? Let me write that. So polynomial, even let me start from yes. So if suppose we have some data points x1, y1, okay. We have some data, okay, and we want to find the best polynomial, as mean to say that polynomial we want, which will be the best fit. So here is, we can generally assume that, okay, let's say that polynomial is this y hat is given. We can assume that, okay, y hat is equal to that, and this is theta 1. I think this is the notation is the same, theta 1. Yes, theta 0, theta 1, theta 1 x till theta n and x to the power n. Now we'll get our matrix, where matrix A is just this that phi is phi is formed by that function. Let me show you that, where it is this phi is this for x, the transform feature vectors phi x is 1 x square. So whatever the data set would be, so actually what is a is actually would be obtained one, where is that, it would be obtained by one that side, and theta 1, that power will go, that is theta x1, sorry, yes, so not theta, phi 1, phi x1, phi 2, phi 3 will go on, and then that y will get here y values, y1, y2, yn, and this is just finding a transpose a, and then theta is equal to y. Where is that formula? A transpose y, and theta would be get by taking the inverse of theta is our theta 0, theta 1, that is that we want, that coefficients. These are the just the coefficients. Even a best example is already given. It is one tutorial is there, very explicitly here it is explained that how will that form the matrix, how will get inverse very slowly, and these are the data sets. So let me show you that this we have some data points, okay, and we want this quadratic polynomial, okay. So that matrix would be formed. This is the matrix how we'll get here, 1 x1 is square, then 1 x2 is square, 1 x3 square, and this is y values, and so you can see it here. We have to find the inverse of that, and x1, y1, x2 values just will substitute there. So here is that, so 1 x is square, 1 x1 is square, then 1 x2 square, 1 sorry x3 sorry 1 x3 square. So if you find the inverse of that matrix and multiply with that vector, we'll get the theta values, and after that we'll just substitute in that polynomial. So this tutorial is enough to understand that topic, and there is no even nothing, it is just algorithm. This is just algorithm, we have to follow that procedure, that's all. In machine learning, generally we learn the algorithms. The concepts are actually now it will be here, eigenvalues and eigenvectors, and then so this regression and this regression, line regression, and this polynomial regression, all are actually kind of algorithm. We have to just follow that. Now we'll move to this eigenvalues, eigenvectors. So first thing is that what is eigenvector? So eigenvalues are actually came from eigenvector. Means the definition came first eigenvectors, then you can say the eigenvalue. So what is the eigenvector? Eigenvectors are we know a kind of a vector, and then if we multiply that with the scalar, it will be scaled. It will be either, so if suppose this is the vector, if I am just multiplying with that alpha, it could be maybe larger or maybe smaller or maybe inverse of that. So it could be of that kind. So if we have such a matrix, suppose we have a matrix, okay, and we got by sudden, I'm just saying, we got a vector v, which I'm just multiplying with that, it would be it would be have like a is a kind of a scalar, means it actually scale that vector. If you multiply that matrix with that vector, it will scale that. So this would be so this will give an idea how to get that v. So this we can send this av to left side, this alpha v, and then what is that a, this is the v same. So we can now take v common, so we'll get here a minus alpha. So how just you can subtract from matrix and scalar, so that means here it would be identity matrix, okay? And then v is equal to 0. Okay, so this is the process. Here from here we are reaching to a point that how we'll get this alpha. So this tells determinant is 0, that means here determinant of this matrix is going to be 0. By this way, if we solve this, we'll get this alpha value. So this alpha value is called eigenvalue. So eigenvalues and eigenvector came first, eigenvector, then you can say eigenvalues came, because eigenvalues are actually first the eigenvectors and then eigenvalues. But slowly, what is that? If we know this eigenvector, we'll get a procedure to get the eigenvector. So this is the way, this is the intrinsic thing in that theory. And suppose, for example, if we take, let's say,
Sir, can you repeat one more time, please?
This one.
Yeah.
Okay.
Eigenvalues and eigenvector, just highlights.
Okay. So what is the thing is that we have, let's say, a matrix, okay, and by luck, I am saying, because eigenvectors are is a kind of, let's say, these are actually very important. So let's say I just got a vector v, okay, I just got a vector v, and once I multiplied with that matrix and that vector, it's behave like it is just scaling that vector, that same vector. By sudden I got a vector, and when I'm multiplying with that matrix, it's behave like that is scaling that's the same vector. If such thing is happening, then we will call this vector as a eigenvector. This vector is called eigenvector, and whatever number scalar will get, that scalar is called eigenvalue. And from here we can now start deducing how we'll reach to that alpha eigenvalue and then eigenvector. So from here we'll itself get the process to get eigenvalue and eigenvector. We can solve this now equation, and this should be 0. Now from here, if we take this vector as out, then it will be a minus alpha, and now this is matrix subtraction. This is a matrix and this is a scalar. So if we it would be on the same you can never subtract two matrices of different order. We want a same order. So that means, and also you are taking this vector out. That means here identity matrix is hidden, I mean to say, and this here V is out, that vector. And this, this tells you are multiplying this matrix with this vector, you are getting 0. That means this matrix have some, some different property. It have some, but it is actually saying that, or it is actually saying that this rank, if you remember the rank of a matrix, so this tells you that rank of a matrix is not exactly whatever the order, it would be lesser than that. That means this matrix is a singular matrix in different word, or different word, determinant of this matrix is 0. This is what it tells you, because you are getting this, once you multiplying this with this vector, you are getting 0. 0 means here 0 vector, okay? It is not a scalar, okay? This tells you 0 vector. Here 0 means 0 vector of whatever the order we have. If we are n is there, then n vector, sorry, n 0 should be. So this tells you that our matrix is singular matrix or determinant of 0. That means let's evaluate that determinant of this matrix, and by this way, if we get this determinant of this matrix is 0, so by this way we'll reach to a equation which is equal to 0, and once we solve this, we'll get alpha values. We'll get some alpha values. If the matrix is of 3 cross 3 order, okay, then we'll get 3 alpha values. Maybe all are same, or maybe 2 of same and 1 is different, or all are same or all are different. So these are the possibility that it could be of all alpha, alpha, alpha. All 3, maybe the roots are actually same, or maybe 2 of them are same and 1 is different, or all are different. So these are the possibility to getting the roots, because this, once you solve, you will get a polynomial of what degree? Degree would be the same of, whatever the order of a matrix. So these things are only happen to a square matrix. Okay, these things will happen only on a square matrix. Means square matrix, it could be of any order, 1, 2, 3, or let's say n cross n. So these things we are actually studying on only square matrix. Okay, and why we are actually doing this? We can see when we do machine learning, maybe your data is, once you form that matrix, maybe of rectangular, but we can add some zeros and add some another features. Maybe something we'll do and try to convert that rectangle data set into the square matrix and do all these process whatever we want. So that's why we are studying only on square matrix, one way you can say. And so because these properties are whole for only square matrix, so we can change our rectangular data set into even that changing of this A transpose is also will use to change in a square matrix form. So these are some properties that we can change if data set is in the rectangular form. Generally, it is in the more real form. Always it would be a rectangular form, but we can change that matrix, whatever data set we have in square form, and then we can start the studying by this way. Or this algorithm, diagonalization will help to get the power of a matrix. Why we are studying these all? It will be easier to know once how many times you want. Let's say you have a matrix, I want to find the 100 times of that matrix. So then diagonalization will help to find that 100 times of that matrix. If you normally you will do on if you say this is a computer, this can done. Okay, this computer could do this, but it will take time. But if you want to make it simpler, then if you change that matrix in the diagonalization, like if you do the diagonalization of that, then it will be easier to getting this 100 times of that matrix. So at least this is the use till here. We'll see later. Maybe once you do the MLP. Sorry,
Sir,
MLP.
can you show what all of these mean geometrically?
Geometrically is that that is what I am saying. Geometrically means anyhow what you are getting, we are multiplying with a vector, it is behaving like a scale. So this is the one thing is that. And geometrically, another geometric thing is that no, this is the only thing. This time I have no idea. No, I don't think there is a geometric representation saying to be this is the eigenvector, eigenvalues is there. I don't think.
Sir, so eigenvector is the same vector that is scaled. It is just scaled, but it is the same vector.
Yes, it is the same vector. There is no change. That's why I am taking this common, right?
And sir, diagonalization, what happens to the vector in diagonalization?
So yeah, so let me finish that. So let me move ahead now. So this is the way to get that. I will get a, so whatever the order would be, that is going to be the, we'll get a equation, okay? Equation, and it would be a polynomial, okay, of that degree. Degree would be of that polynomial is whatever the order of that matrix, and we'll try to solve that polynomial. We try to find the roots of that polynomial. If it is degree is order is n cross n, then you will get a polynomial of degree n, okay, alpha n plus, let's say something is there, alpha n minus 1, and this is equal to 0. Okay, we try to solve that and try to get the root of that polynomial. Those roots are here, alpha, beta, maybe all are same or maybe different. Okay, so once we got this, then we'll follow a procedure to get the eigenvector. So what is that? Let's say I got a value. Okay, let's say I'm just got a root here, alpha 1. So now what we can do, I will do the same. Okay, this is, I will do this, or maybe yeah, I will do this, and now what I will do, I will try to find the null space of this. What is the meaning is that a minus alpha 1 I, okay, and time, let's say I will try to find the null space of, I hope you know that how to find null space of this. This is equal to 0 vector. And now try to solve this and reach to a values of x, y, z. So generally what is that, you will get a null space, it is a space. So what it means that you will get a infinitely many, you will always get a, this will not contain unique solution, okay, as the determinant of this matrix is 0, so you will not get a unique, it will have always a infinitely many solution. So either a variable, no, x, y, z, maybe any one of them will be independent and others may be dependent. We'll see with an example. Okay, so let me explain by the simple example. Let's say you have a matrix 1, minus 1, 1, and let's say 0, 1, and minus 1. Okay, and let's say 2, 1, 1 is there. Okay, suppose this is the matrix I have. So what I will do, I try to find the roots of that. So let me make it easier, bit easier. Okay, let's say 2 is here. Okay, suppose this is the matrix I have. Now what I will do, I will try to find the root of this. So let's say this is alpha time I. So means alpha time identity matrix. And I will try to find the determinant of this matrix. So this would be our this would be of, if you do this will be of 1 minus alpha minus 1, 1, and 0, 1 minus alpha minus 1, and this is 0, 0, 2 minus alpha. We'll get this matrix, and I want to find the determinant of this. Okay, so what this is going to be, if you do determinant of, so directly we can take this row. Okay, and now we can do, so this is going to be 2 time minus alpha, and this would be of 1 minus alpha square. Yes, that's all. This is equal to 0. So determinant of this is going to be this, and this is equal to 0. And we'll try to solve this for this one. So here this gives that alpha is equal to 2, and other values are alpha is equal to 1 and 1. So it have 2 roots are same and 1 root is different. Now what is the next process? Next process is that I will try to find the A minus alpha I. Okay, I will try to find the null of this. This is the roots of that. So let's take one by one each. Let's take each root one by one and find the null space.
Sir, your screen is not visible.
Sorry?
Your screen is not visible.
It is visible, sir.
I think, yeah, it is visible actually. Yeah, I can see here. So you can just pin, you can search and then pin. Otherwise, I can let me do once again try to represent it again. Oh, it is resumed, I think. Let me stop.
In between, someone is also presenting the screen.
Okay, yes, that's why it resumed. Yes, yes. Now it is fine, right?
Yes, sir.
So whatever till here it is, I hope all of you have seen this, right?
Yes, sir, got it.
So then let's do the next step. We'll try to find the null space of this. So I have this matrix 1 minus 1, 1 minus 1, 1, 0, 1, minus 1, 0, 0, 2. Okay. And then alpha I am taking, let's say 2, and identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. So this would be of, this will be minus 1, minus 1, 1, 0, minus 1, minus 1, and 0, 0, 0 will get here. And now what is going to be the null space? The process is, let's say, this x, y, z is there, and this is 0 equal to 0. So from here, this tells you that y minus z is equal to 0, and next is minus x minus y plus z is equal to 0. The first one will give this equation, the second one will give this equation. And now from here, this tells you y equal to minus z. This will give y is equal to minus this, minus z. And this is what? Minus x. In place of y, we can write minus z. Sorry, in place of that, we can write minus z and then plus z. This is equal to 0. Minus z. Yes. So that this tells you minus z is equal to, sorry, minus x is equal to plus 2z is equal to 0, and this tells you x is equal to this will give x is equal to 2z. So we have this system have we got the values here. What? X is equal to 2z, y is equal to minus z, and z is equal to whatever. So z is equal to z itself. Now this will give the eigenvalue. This tells you the system has infinitely many solutions.
So 2 minus 1, 1, na? Eigenvectors for lambda is equal to 2.
2 minus, sorry, so this now what is that? We can assume z is equal to 1. Okay, we can assume generally z is equal to 1, and in that case we'll get here 2 minus 1, 1. So this is the one eigenvector. Okay, this is the eigenvector corresponding to this eigenvalue 2. Okay, now let's do for the next one, for 1. So for 1, if we'll do, so this is, we have a matrix 1 minus 1, 1, and this is 0, 1, minus 1, and 0, 0, 2. Okay, now 1 is the same, 1 will be, means I am just subtracting identity matrix. Okay, and this will give 0, minus 1, 1, 0, 0, minus 1, and 0, 0, 1 is there. So this is the matrix we got. Now let's find the null space of this. So to find the null space, we'll just multiply a general matrix and equate to 0. This is generally process, I hope you remember. to find the null space. So this is one. So whatever we got here, this is one vector in the null space. Okay, this is a one eigenvalue with corresponding to this. So other eigenvalue, it will be just of a scalar time that. So we don't want, we want just a one vector. So after assuming that whatever infinity we are getting that free variable z, let's assume that z is equal to 1 and others value will easily get, and we'll get a corresponding one vector. So let's keep this one vector here. Now let's do here. So this will give here this is minus x plus y equal to 0, y equal to 0, and z is equal to 0 we got. I think I'm making an error here.
So minus y plus z is equal to 0, no?
Minus y plus z.
So first equation.
Minus y. Yes, yeah, that's yeah, okay. This will give here minus y plus z is equal to 0. Okay. And here is, okay, z is equal to 0 we'll get here. Okay. And this is minus z is equal to, this will give minus z is equal to 0. This will last one will give z is equal to 0. So by this way we got that, okay. So from here we got that z is equal to 0 and y is equal to 0. So substitute here z equal to 0, we'll get y is equal to also 0. Our variable x is free now. There is no important. Now to get the null space, yes, x is anything, any real number. So by this way, this tells you that let's assume x is equal to 1 now. So if we assume x is equal to 1, so x value is 1, y value is 0, z value is 0. So this is the eigenvector corresponding to 1. Okay.
Sir,
Yes.
in first case, we need not to put again that for z is equal to 0, 1.
No,
One
is
set.
here for this one.
Yes. One set z is equal to 1 and again putting z equal to 0 for play.
No, why one set is z is equal to 1, another set is y we will not take because there is no two independent variable happening, right? Only one, z is free. Only z is free. So there is only one, z is free, right? Here is only everywhere is z is free. Here our case is x is free. For this case, x is free. So here is only z is free. So once we'll only one, z is equal to 1 assume, and then we'll get the all other value that is going to be your eigenvector. For example,
If two variables are free, then
if suppose
we'll
the case is that this one, x plus y, okay, and plus z is equal to, let's say 2 is there, okay, or maybe this case is there, okay, because if you want to, here I didn't get a two variable case here. I will, this is one interesting example, okay, I will tell you that what is here. So this is the case here, let's say this is equal to 0. So in this case, you have two free variable, minus y, minus z. So we'll get this one. So we have two free variable. In this case, now your eigenvector is going to be, we'll substitute here, we'll assume y is equal to 0 and z is equal to 1. For that, we'll get eigenvector what? Minus 1, 0, and 1. This is one eigenvector. And now we'll assume y is equal to 1 and z is equal to 0. In that case, we'll get minus 1, 1, and 0. So if you have two free variable, this will give two independent eigenvector. If you have two free variable, because this will tell you, if you compare, these two are going to be independent. But here is only because two free variable, two means two independent variable you are getting. Because of that, you are getting two independent eigenvector. But here
sir, then in above case, why we chose z equal to 1? Why not z equal to 0?
So because 0 eigenvector, 0 is obvious. 0 is always going to be an obvious eigenvector. So we don't want. We want a non-zero vector. Okay? We want a non-zero vector. We don't want a zero vector. Because of that, here we can, if you are saying independence, then we can assume x is equal to 0 and z is equal to also 0. In that case, also we'll get a 0. That is
So
fine.
zero is always there.
0 is always eigenvector, okay, for any matrix.
Sir, excuse me, sir. Sir, hello.
0 is going to always
Is your voice audible?
No.
Am I audible right now?
Yes,
Yes,
sir.
sir.
I just got disconnected. Okay, I don't know how it is. So I was discussing this one. I told you this I told you or not. Alpha have one eigenvalue. This one eigenvalue as 1. Two repetitive eigenvalues, but we are getting only one eigenvector. So will this matrix be diagonalizable? This matrix, our A matrix, will this matrix be diagonalizable? Anyone? Anyone? Any idea?
No, sir, not
Will this
diagonalizable.
be diagonalizable?
No, sir.
Why it is so?
Because you are
Why
same
it
eigenvalues.
is?
Eigenvalues
No,
are
same
same.
eigenvalue, that's fine.
And since
Same,
they
there
are,
is no issue with the same eigenvalue. Maybe in a matrix it is diagonalizable and all eigenvalues may be same. There is no issue with that. But
no, in that case, we can't get
uh,
linearly independent eigenvectors.
we are getting linearly independent eigenvector. These two, so this one is independent to this. You can check that. See that here is entries are 1 0 0 and this is 2 minus 1 1. What is that? If you check, this is going to be independent. Any other reason? This is not enough. This reason is
Sir,
not
but
enough.
we also
The
need
order of the
for
matrix
another one,
is
right?
how will we will be having two columns only in this case,
Yes,
right?
that's the one. Only have two columns. We want another eigenvector. Somebody says that also. We want another vector.
Yes, sir.
We have this one. We got this, and from 2, and from this one we got from 1. But another eigenvector we want, and we don't have that another. Why? Because now these eigenvectors will try to fill in the P matrix. that the P matrix or whatever that A is writing to be in this in diagonalization form, that is called a spectrum. Also, kind of word is used. So this is P A P inverse. I think inverse is here or is correct here or here. Both are generally work. Okay, these are symmetric. So actually, it is going to be a inversible matrix. So there is no issue with it. So maybe if we are writing here, that's fine. If we are writing here, both are actually going to be true. So there is no issue. So for this matrix P, entries would be filled by the eigenvectors. So let's say this is V1, this is V2. So we got this V1 as -2, -1, 1. Okay, and this is V2 is 1, 0, 0. But this is another column we want. How we feel this in another column? There is no
Not making
eigenvector.
a square matrix.
Sorry.
Not making a square matrix.
We want a square matrix. This is a rectangular. So what is going to be that? So if this thing is not happening, then we will say our matrix A is not diagonalizable. So this matrix A is not diagonalizable. Okay. We want a diagonalizable. To get to matrix is diagonalizable, there should have, if it is a 3 cross 3, then it have 3 independent eigenvectors, but we are getting only 2. So that's the issue here.
This implies distinct eigenvalues.
No, even same eigenvalues could have 3 independent eigenvectors. Even same, I will give some another example,
Sir,
and you can check even.
But in lecture it is said if eigenvalues are different, then we'll get definitely linearly dependent eigenvectors. So
if it have
converse
different eigenvalues, which see, if the eigenvalues are distinct, then it's give the COT that your matrix is diagonalizable, because you will always get 3 distinct eigenvalues. Sorry, eigenvectors. But here is the eigenvalues are not distinct. One is 1 2 times and another is 2. So it is a repetitive. So in this case, it is not diagonalizable, because I will give you another example. Okay, I will give which is diagonalizable. Okay, so let me give another example. You will see there itself.
Sir,
Yes. Yes.
Sir, I have solved a question for the diagonalizable, which I get the eigenvalue, 2 eigenvalue are the same, but I get the matrix is it diagonalizable?
Yeah, we will get here P, proper P. When next eigenvector will get here, I will give an example. Okay. So let's do for this one, or let's say this is here. Let's make it 0 also.
So take an example of
I will show you. Okay, I am just giving a very quick way. So let me show you that how it is. Maybe I will just okay, for you can not use this. I will suggest you not to use, but singular value decomposition calculator is there. Okay, I will use this, but I will suggest you to not use this calculator. Okay, I will just show you an example where the eigen values are, or maybe let's say calculator is called Gauss elimination. Okay, calculator. Not this one. I don't know what is the exact. Let's say this. This is one I have. Eigenvalues calculator. Something its name is there. So let me give an. Let me show you. This is, let's say, 1, and let's say 0, and then 1. Suppose these are the entries we have. 0, 0, and let's say this is 2. Okay, and if I want to find the eigenvalue of this, so see that the eigenvalues are 1, 1, and 2. Okay, and if I will try to do diagonal matrix for this, so see that what will happen now. So the same process. I hope all of you are able to understand this. I'm just giving an example. So see that this a minus alpha time, if you see, we'll get the roots 1 and 2. So okay, so see that I will try to what? A minus lambda I. So lambda is our 1. For lambda 1, okay, my cursor is, all of you are able to see, right? This cursor.
Yes, sir.
Okay. So this lambda 1, which is one root eigenvector, sorry, eigenvalue, I am now try to get the null space, means eigenvector. So A minus lambda I will do this, we'll get this matrix 0, 1, 1, 0, 1, 1, 0, 1, 1. Okay. Now what is that? A minus lambda I times B. B is x, y, z. Okay. And try to solve this system of linear equation. And if you try to solve this, see that what is happening here, we are getting this system of linear equation. So let me show you here itself. So I have this, once I will do that matrix, I will using here, once I will do this one, A minus 1i and eigenvector x, y, that general vector to get that eigenvector. So this is going to be, we are getting this matrix 0, 0, 1, 0, 0, 1, 0, 0, 1. Okay, this matrix I am getting, and this is x, y, z equal to 0, 0, 0. Okay. Now see that. Now if you solve, this will give always z is equal to 0. Okay. If you solve this, we'll get this giving, if you do multiplication here, this will only giving z is equal to 0. So you have two independent. Now x, y is independent. From here we are actually getting x, y as the independent. So x, y is free now. So now we can give x equal to 0, y equal to 1. We'll get a vector 0, 1, 0, because z value is always 0 here. Now this will give one vector, and now if you assume x is equal to 1, y equal to 0, so in this case we'll get here 1, 0, and 0. Z is always 0. So for what is our matrix? Let me take our A is, what is that A? So where is that? Not this one. Our A is 1, 0, 1, 0, 1, 1. Our A is 1, 0, 1, 0, 1, 0, 1, 1. Okay. 0, 1, 1, 0, 0. This is our A. I got the eigenvalues. Okay. Lambda values, eigenvalues 1, 1, 2. So I use 1 to find here eigenvector. So by this way, I reaches to this, and I got two independent eigenvector. You can check, these two are actually independent. For one itself, I am getting two independent eigenvector. Previously what? Previously for one which is repetitive itself, but getting only one eigenvector. So that's why our matrix is not diagonalizable. But here for one itself, I am getting two independent eigenvector. And even two, now for this two, if we try to get, so let's back to our exercise here, which is in calculator. So for one, we are getting two independent eigenvector, this one and this one. And now let's do for this. See, lambda 2 is equal to 2. If we do this, we are getting this eigenvector 1, 1, 1. So if we let me write that, for lambda 2, I am getting eigenvector 1, 1, 1. So see that for our matrix A, I am getting three independent eigenvectors. See the reason here. Here, no, not reason. See that the last time and here this. Roots are repetitive, but getting three independent eigenvectors. So our matrix, this A is diagonalizable actually. Why it is so? Because I am able to find this matrix P and that's the diagonal, and this P inverse. What is this P? P is now one by one I will fill that eigenvector. So 0, 1, 0. This eigenvector I filled. Next fill this one, 1, 0, 0, and this one, 1, 1, 1. So I get a square matrix, which is actually three. All are actually, all are independent. So this matrix is actually invertible. So that we are able to get here P inverse also of that. And this diagonal is nothing but the eigenvalues. The diagonal is nothing but the eigenvalues, and this P inverse we can get. We can calculate the inverse of this. Clear? Is this clear? Maybe eigenvalues is repetitive, but eigenvector will be a different eigenvector will get.
So in this case, even if the eigenvalues are same, we are getting independent eigenvectors. But
independent.
We can also say that strong claim is that if we are getting eigenvalues as distinct, then we'll definitely get X matrix. I mean Xn vectors, which
if you are getting distinct, then it's giving surety. Yes, correct. It's giving surety that your matrix is diagonalized. Correct. Okay. So this is the reason, and why I will say matrix is diagonalization. The reason is only this one. I am able to get the independent eigenvector, so that I am able to form our matrix P. P is very important. How I will feel or how I will get this P? P is nothing but actually I will write the eigenvectors in column wise, and that is our P. And the diagonal is nothing but diagonally we will write the eigenvalues, and in rest places I will just fill 0. And inverse is the inverse of P. That P inverse is the inverse of P. So A is now this. Okay, A is nothing but this. And now why I'm saying this? What is the use now? So if we do A power 100, or let's find A square. Okay? So A square is what? P inverse, or let's say P is there, P D P inverse. Okay, and I'm doing the square of this. So if P D P inverse into P D P inverse, what is happen now? What will happen now? So this P D, now these two will multiply, P and P inverse will multiply. It will become identity, and then P inverse. So then, sorry, identity, and then this D is here. This is now this P identity. If you do multiply here, this will be D square and P inverse, and here is A square. So see that that's why the diagonalization is important. If you do a square this side, here just a D square, and P inverse will be the same. So if you do A power 100, so it is just P D power 100 and P inverse. And see, this is diagonal. So what is that? If it is, we'll do here square. Okay, if you do a square here, it is just square here, here, and here. That's all. Just if it is 100, so if you have diagonal this A 0 0 0 B 0 0 0 C, and I want to find 100 of this. So what is that? A power 100 0 0 0, B power 100 0 0 0, C power. That's all. That is the property of diagonal matrix, and that's why we try to change our matrix in diagonal form, so that we are able to get the higher power of our multiple. Many times we can do the matrix multiplication.
Sir, while forming the matrix P, order of the columns does not matter, right? In which order we take the columns?
What is that? No, all order will not matter. Okay, but you have to keep in mind. See, these two are actually came for the eigenvalue 1, so that's why this 1 and 1 is here. Last one actually came from the eigenvalue 2, so in last I wrote. So at least this should be clear in that order. I should to write that while filling this diagonal.
Okay, sir.
Even you can check also. Okay, you can check. It is, you can verify. Just find the inverse, multiply this. This will be always same. So So just keep in mind that I'm first row I'm keeping here. So corresponding that eigenvector I will fill here. If I'm second eigenvector filling here, so corresponding that eigenvalue I place the second row. And this is the eigenvector corresponding eigenvalue will fill in the last. So this should be keep in mind.
Okay, sir.
Okay. So this is also the diagonalizability also. All this is the only thing. Now only the orthogonal diagonalization is remain. So this is just a property what? If your matrix is symmetric matrix, okay? If your matrix is symmetric matrix, then P would be, P will be a orthogonal matrix. So what is the orthogonal diagonalization? This is itself the matrix property. If our matrix is symmetric, what is symmetric? A should be A equal to A transpose. If you do the transpose of that, it will be the same. So if our matrix is symmetric, okay, so in that case, whatever P will get, P is going to be a orthogonal matrix. What is the orthogonal matrix? Orthogonal matrix is that if you do
Dot product is
P
zero.
and P, no, P and P transpose, it would be identity matrix. P and P transpose do, if you do this, multiply this, you will get the identity matrix. That is the property. So what it means that it implies that your inverse is what? Inverse is the transpose, just a transpose of that. So what it means that, so our matrix A is actually I am writing PD inverse. So in place of inverse, I can just write PD P transpose, because inverse is our just a transpose of that. And these things is only happening because of A is our symmetric matrix. And one example, not example, one property I am saying, if your matrix A is symmetric, no, then it is always matrix. If matrix A is symmetric, then it is always diagonalizable. Just a second. Okay, so what I was saying, if matrix is symmetric, no, in that case it is always diagonalizable. What it means that it will be not the case that sometimes I am getting independent eigenvector, sometime I am not, like here is the case. For this case I am getting only one eigenvector for the repetitive. But if matrix is symmetric, no, in that case even all roots are, no, all eigenvalues are repetitive, all three, 1 1 1, but always you will get a independent eigenvector. You can check, we can verify. I will do an example on that. So we can verify that, okay, always it will get eigenvectors. And now I will fill in that to get P. And if you check, this is going to be a orthogonal matrix. We'll try to do this. Okay. And so this is going to be orthogonal matrix. And that is the only thing. That is the thing now remain. Am I audible? Is it clear?
Yes, sir.
Is it better now?
Yes,
So let's do an example. So I will do again on calculator to do a fast way. So let's say this is -1 is there, and let's say this 1 is there. So this would be -1 and 1 is here, and this is 1 here, and this would be 1 here. So suppose this is the matrix. This, if you check, this is a symmetric matrix. What is that? Say that this is 1 minus 1 and 1, and see that this row and this column is going to be the same, 1 minus 1 1. If you take the second row, this -1 1 1, so the second column is going to be the same. Second row is as the second column, and third row, sorry, this third row is this 1 1 1 2, and third column is going to be same. That means what? If you do the transpose of this, it is going to be the same. So this is a symmetric matrix. Now see that what is going to be happen now. So let's do the diagonalization. So this is C. It is always going to be diagonalizable. See the detail here. Okay. So if you see the detail, the roots are actually distinct. Okay. So this, in this case, our roots is actually distinct. Let me make a repetitive root. Let me fill the entries where the roots are actually all identity matrix. Ever you think that identity matrix 1 0 0 0 1 0 0 0 1, this is a symmetric matrix, correct? This is a symmetric matrix, and if you find the root of the eigenvalues are these 1 1 itself. All roots are actually same 1. And if you find the eigenvectors are nothing but this column of this. Eigenvector are going to be 1 0 0 0 1 0 and 0 0 1. These are going to be the eigenvectors. And matrix P is going to be itself identity. P, if you check, this P is identity. So identity matrix is an orthogonal matrix. You can do find the transpose of that or inverse of that. Inverse of identity is inverse itself. So what it means that if you, whatever the P you are getting, which is nothing but the P transpose. So let me try it with another example, or even no, let me search on Google. Then it would be simply, you can see symmetric matrix with repeated eigenvalues. So maybe it may give some example. I just want that example. It is asking to download. So this one, like this, -1 -1. Okay, let's do this, -1 -1 0. So let's fill in this even for the 1 -1 0. So 1 -1 0 is there, and next is -1 0 2, -1 0 2, and next one is 0 2 3. 0 2 3. So if we do the diagonalization, even this one is also distinct. distinct eigenvalues we are getting. I think 1 1 1 matrix is there. All are 1 1 1. I think that was going to be all are 1 1 1 in that case. Maybe let's do for this one. So in this case also roots are different. So no 0 0. See that this is the 0 0 0 3. So let's see the detail of it. So see the roots are actually eigenvalues we are getting for 1 1 1. This matrix. This is a symmetric matrix. Okay. So if you do the find the root eigenvalues of that, so this is the formula a minus lambda I and find the determinant. We'll get this polynomial. This is generally called characteristic polynomial also. Okay. And by this way, we'll get the roots 0 and 3 only. So 2 times 0 and 1 is 3. So see the 0, if you use 0, we'll get here 2 independent eigenvector, because as symmetric matrix is always diagonalizable, that means always you will get the different means independent eigenvector also. Means if it is a 3 order, that means 3 eigenvectors you will get. Even it is repetitive also in that case. If it is repetitive, in that case also will get. So here is 2 independent eigenvector will get for 0. And for 3, if we do for 3, 3 will give here 1 eigenvector, which is 1 1 1. So by this way, we'll get the P. We'll fill here one by this. We'll fill here to get P. Now if we check, this P is actually orthogonal. If we check this P is going to be orthogonal. So let me take this this P, which is so let me show you that it is going to be orthogonal. So we got this P because eigenvalues are this, eigenvectors are this and this. Now if we check, this is going to be orthogonal to each other. So how we'll check this? The columns are going to be orthogonal. So if you take any two column and multiply to each other. So if you multiply these two, what you will get? So if you take these two columns, this one, and if you multiply, this will give this one, which is -1 1 0, and second one is -1 0 1. If you do dot product, multiplication means dot product. So this will give what? 1 and times 1 plus 0. 1 plus 0. Okay. Just a second. Sorry. One thing I missed. I just made a mistake that. Okay, so there are actually two properties. If the roots are, so let me explain that. That's why these two are not independent. Not orthogonal. Okay. So one thing I just missed that. Okay, what I am missing that if matrix A or A matrix is symmetric. Okay, symmetric, and root of this eigenvalues are 1 1. Let's say I'm saying 1 1 and 2 is there, or our case is 3 is there. So whatever the eigenvectors I will get for this one, because we'll get two independent eigenvector, okay, -1 0 0, so minus 1 1 0, and another is minus 1 0 1. I don't know, I am just speaking. Is this clear? Please stop me if I'm going fast. I don't know how it is. Understandable or not? Am I audible?
Yes, sir. Understandable, sir.
Please stop me if I am going fast, or uh, all of you are not getting anything. Anything is there, please stop me. Otherwise, I will go and I will not know
Yes, sir.
that
Yes.
you all are under.
Lecture is going smoothly, sir.
Okay. So if the roots are same, so we'll get two independent eigenvector. But if they are same, then they are not orthogonal. Okay, they are not going to be orthogonal. If all are different, let's say this is 2 and this is 3, all are different, mean distinct. In that case, eigenvectors are going to be orthogonal. See that, for example, you can check here. These two are with respect to the same eigenvalue 1, and this is for 3. So that's why if you check, these two are not orthogonal. That's why here when I was doing the dot product, I was getting 1 plus 0 plus 0, which is 1, not becoming 0. So these two are not orthogonal. But if you check for any one of this and this, the distinct one. So if you check, if you do the dot product, minus 1 0 1, okay, dot product with 1 1 1, if you do this, this will give minus 1 plus 0 plus 1. That means 0. So for distinct one, we'll get always orthogonal eigenvector. But for the same eigenvalue, we'll not get the orthogonal eigenvectors. Okay. But this is one property that is called spectral theorem also. Okay, that if matrix,
Sir, one doubt,
matrix,
sir.
yes.
Like we get eigenvalue 113. Repeating the value of 1, like we
Yes.
find the eigenvector only for 1, na? Like we get only one eigenvector for 1 or 2, sir.
No, two eigenvectors we got, right? For one eigenvalue we got here two eigenvectors.
It means that nullity for the eigenvalue of 1 is equal to 2.
2, correct.
Okay.
Null is specified. Nullity for eigenvalue 1 is 2.
Okay.
So what I mean to say here, if the eigenvalues are same, okay, in that case eigenvector for a symmetric matrix, if eigenvalues are same, in that case I will surely get eigenvector. Okay, even all eigenvalues are going to be same, three eigenvalues are going to be same, I will always get three independent eigenvector, but those three independent eigenvector may not be orthogonal. Okay. So it means that symmetric matrix is always diagonalizable, but in that case, here whatever we are following the procedure in this way, we are not getting the orthogonalization. What is that? Orthogonally diagonalization. We have to do something. What is that? What we can do now for in this case, if these two are not orthogonal, then we'll use the Gram-Schmidt process to make them orthogonal. And then in that I will fill in P, then get, but we don't want this time, we just want two distinct eigenvalue. Here we just studying the diagonalization here. Okay, just studying the diagonalization. That means if the matrix is symmetric, in that case it is diagonalizable. If you see the spectral theorem. So let me write many times. I'm just repeating the word. So what is that? If matrix A is symmetric, okay, then or implies A is diagonalizable. I hope you may got the meaning of diagonalization. Why I am saying, because I want just P, and if symmetric is there, then I will always get P. But there is another, this is another implication, is that A is also orthogonal, diagonalizable. Okay. So to get the orthogonal P, we have to do Gram-Smith process. Okay. So we'll see later. I think sir taught the Gram-Smith process. Orthogonalization is there, so I think already taught. So we'll do what is the process that we'll try to use the Gram-Smith process. We'll change these two in orthogonal. It is already orthogonal, and only apply on these two and try to get the orthogonal, and then we'll form the P matrix.
Sir,
Okay?
after changing the orthogonality of the two vector, it is surety given that the after changing the vector in orthogonal, it is also orthogonal to the third vector.
It is not. Yeah, actually, for that we have to change. No, so
we have to change that all three.
We have to do all for all three. Yes,
Oh.
I'm not giving the surety. I have to do all for the all.
Excuse me, sir.
Yes.
Sir, if eigenvalues are distinct, then they are orthogonal.
Then they are orthogonal. Yes. Then directly we get
same,
orthogonally diagonalizable.
And
Yes.
if they're same, they are not orthogonal.
So then they may not be orthogonal. Correct.
Okay, sir.
So last time one question is there. Okay, I think in quiz 2 there was a question, or maybe in quiz 1 itself, or maybe in 10 somewhere is there that it is given that matrix is symmetric. Okay, matrix is symmetric. Okay, and but just a symmetric matrix. No more information. Is just a symmetric matrix, and said that it is no. So just a symmetric matrix. Then here is there. Then eigenvectors are orthogonal. So is this statement is true? If just a symmetric matrix, then eigenvectors are orthogonal. Will this be true?
Yes, sir.
No, if the same, what is going to be in the same eigenvalues are going to be same in that case? What is going to be in that case? Then may not, right?
Oh.
If the same as here, 1, 1 is there, in that case, the eigenvectors are not orthogonal. So that's why this statement is not always true.
It means the sir eigenvalue is not be distinct.
Because in this case, here I'm not saying any more information. I'm not saying distinct eigenvalues. I just said symmetric. So symmetric matrix may have the same eigenvalue, may have the distinct eigenvalue. But in this, both are included. So both are included. So this statement, how it could be true? If the same, then how it could be true? So that's why it is not always true. If I said here the one extra word, symmetric matrix with distinct eigenvalues, then it is going to be always true. Then in that case, eigenvectors are always orthogonal. Okay.
Yes, sir.
Okay. So even if anybody want to use this calculator, you can use. That is for practice you can. But if you do yourself, then it would be good. The website name is Matrix Calculator. Something name is there. This is
Can
a
you
good
share
one.
the link?
Matrix Calculator, just Matrix Calculator. Many things are there. If you do Matrix Calculator, many things it will give: rank, transpose, row, diagonal, decompose. Many things are there. Multiplication, addition, determinant calculator, eigenvalues calculator. This you can use for verify your answer. Try yourself, then verify that I am correct or not. Okay. So that's all in this week also. Nothing now remain. Orthogonality we did. And yeah, orthogonal diagonalization. Fibonacci is just an example. This is solved that using the diagonalization. We can solve the Fibonacci sequence, and diagonalization is done. So now nothing is given from to discuss. I just all did a summary kind of. So anyone have any kind of doubt? I'm just want to listen. Any doubt? Any kind of doubt in your mind is coming? Please let me know. I will discuss.
Excuse me, sir.
Yes.
So there can be infinite eigenvectors for each eigenvalue. Is this statement correct?
Yes, yes, yes. Because eigen null space is a space. So for one eigenvalue, infinitely many eigenvectors are there. But those for one eigenvector, sorry, for one eigenvalue. Okay, let me write here. For one eigenvalue, like let's say eigenvalue is 1, I will get infinitely many eigenvector. Okay, but those eigenvectors will not linearly independent. They are dependent. Okay, they are dependent.
Means of span is always 1.
Yes, in span is always 1. Yes, correct. So actually, now it is just a small thing. Actually, that null space of that a minus lambda I, null space of that is called the eigenspace. That null space is called the eigenspace. In more, if you do the BSc mathematics or MSc mathematics.
What you told, sir?
Eigenspace. That word null space is called eigenspace in that case when you are finding the null space of a minus lambda I.
Sir, span not necessarily should be 1, right? Because if we get for one eigenvalue, we can get 2 distinct eigenvectors.
In that
right?
case, yes. In that case, I am getting 2 distinct, not two linearly independent eigenvector. So that means your nullity is 2 in that case. So eigenspace is of 2 dimensions in that case called. Correct.
Okay, sir.
If 2 eigenvalue is same, sir.
So in that case, what is the meaning is that if suppose I am getting for one same eigenvalue, I am getting 2 here. One is 2 eigenvectors, this one and this one. So in the combined form, we'll say the null space, which is eigenspace also, null space, which is eigenspace or null space, eigenspace also called, is going to be 2-dimensional.
Yes, sir. Span is 2, sir.
Span is basis called. Basis have 2 vectors.
Sir, span or basis is different.
It's a bit difference. There is a very small difference. Is that what is a span? A span contain
Minimal subset, it is called. Like
in a span may not be linearly independent. Okay, may not be linearly independent. But in basis, always whatever vector it will contain, it will be always independent. That is the only difference. Okay, so that means basis is the subset of span. Basis is the subset of span which collect vectors. Using whatever the vectors I am try to get the span, those if you collect those all will be the subset. Sorry, basis is going to be subset of this. Using whatever the vectors actually try to get the span. There are very small differences there. Span may contain whatever we are going to use to get the span. Those vectors may not be independent, but in basis always independent vectors.
Okay.
Okay. Any other doubt?
Yes, sir. Why we use diagonalized thing of any matrix?
That is what I said, no? 100 times if I will do, or 500 times I will just want to do matrix multiplication. So diagonalization will help, right? I just showed you with an example that it will be easier to compute the, if I want to find a square, I'm just writing P dP inverse, okay, twicely. Twicely means P dP inverse into P dP inverse. And
Like it is the same as the like a square. Like we have to compute the square of a matrix in
and
that
that, yeah,
TP
any power of matrix, and then diagonalization will help.
like in calculation.
Yes, yes, in calculation, yes.
Okay.
So this is one mathematical use, but this time I am unable to say you what is the use in this machine learning. But the in mathematics, the use of that diagonalization is finding the power of matrix.
Yes, sir. It is like easy to calculate because it is only diagonal elements are present
You
there.
have to do the square, cube 100 times of just on the diagonals.
Yes, sir. It is easy to calculate.
Yes.
Sir, if possible, can you please go through Fibonacci example once?
Okay. Fibonacci is for that. It is just a process. There is no different method. Actually, what is that? No. Again, it will be used there. Eigenvalues and eigenvector. This is one example to solve Fibonacci. What is that? Anyhow will convert. So, see, Fibonacci is the recurrence sequence. So Fibonacci sequence is a kind of recurrence. We'll try to convert this in a matrix format. And how we are getting this matrix, we can see it here. How it is. So in this form, this Fibonacci sequence is converted in, see that, in the matrix format. Now when it is converted, so this whole Fibonacci now, see that it is converted in the matrix format, in the system of linear equation format. Now once we do this, then now I will use this A, whatever, try to convert that in matrix format. I will use now A to get how it is now. See that now our A is the coefficient matrix A is this one. Then is a solution to UK plus 1 is equal to AUK. What is that next? Okay, now the diagonalizability will use. We'll try to diagonalize that. Why it is so? Because if we want to find the UK term, that yeah, where is that? We try to convert. Once we converted this, okay, just a second. Okay, I was just missed that. UK is our this one. UK is, that's why I'm thinking, where is UK? UK is FK plus 1 and FK. And UK plus 1 is now UK plus 1 become in this format, okay, which is nothing but this system of linear equation. Okay, yeah. So yeah, so UK is UK and UK plus 1 is UK plus 1 is equal to in this fashion, which we can write here also, as here it is written. Now, what is that? If you want to find UK, UK is nothing but a power k times u0. uk is equal to also nothing but a power k times u0. How it is? The reason is this one. u0 is equal to what? c1, x1, c2. This is okay. This is a basis. So this is, polynomial space now. Sir is actually playing on polynomial space where x1, x2, xn is a basis. So here u0 is c1, x1. No, not polynomial space. Sorry. c1, x1, c2, x2, cn, xn. So a u0 is going to be c1 a times x1, cn a times xn. So uk, by this process, if you do by this process, this give you uk is equal to a power k u0. What it means that I actually anyhow try to convert this to find the power of matrix. That means any term uk is just finding by the whatever the matrix coefficient matrix I got, just find the power of that and starting time u0 vector. So to find the a power k, let's do the diagonalization. That's all. So that is what sir is here now. We'll try to get the eigenvalues, eigenvectors. So eigenvectors is going to be this. Sorry, eigenvalue is going to be this number. This is called golden ratio also. Golden number, golden ratio, 1 plus root 2 and 1 minus root 5 by 2. Okay. So once we got this, so now you know the what is the use of power. That is, once we got the diagonalization, then a power k will be easily calculated by just on the diagonals. 1 plus root 5 by 2 power k will go up and just multiply it. So this is it is, I hope, able to whatever I am saying, is that clear? I don't know how it is. I'm just giving a summary, okay? Because in lecture it's miscalculated.
One thing, sir. Can you write the formula of that video, sir?
I can write, but each time I have to.
Main formula of the thing, sir. Solving Fibonacci sequence.
Okay, just a second.
Because sir taught that I did not understand very well.
In starting or in the last?
From the first, sir. Because sir.
Okay. Here itself, how sir is forming the system of linear equation.
Yes, sir.
Okay, so just a second. Let me explain itself this one. So first thing is, what is Fibonacci? We know already that any terms already get from the last to adding the last two. And from here, what is happening? This is true. This is the one. Sorry, this is F. Okay, sorry, F. This is F here. So this is already we know. Okay, but this is also true. Fk plus 1 is equal to the same Fk plus 1. This is already true. This is Fk plus 1 is what? The same term I'm just writing twice. I'm actually trying to convert this equation in the system of linear equation. So what it means that now this we can think F yes. Okay, so F k plus 1 and F k plus 2. So see that how it is. This is our variables. These are our variables. This is right, left side, and this side is the equation. What it mean that? What is that? See, this side is 1, and here what is that? Fk plus 1, 0 time Fk I can write 0 time Fk I can write. So now if I want to write this equation in the system of linear equation, how I will write this? Fk plus 2, Fk plus 1. This is equal to matrix multiplication of the coefficient. Here is 1, here is 1, here is 1, here is 0. So 1, 1, 1, 0 time f k plus 1 f k. Let's open. If you have doubt this, so what it means is just open this. This one is multiplied like this. So this is f k. So here this tells you that this you will get what?
Fk plus 1 plus Fk.
Fk, and this should be just Fk plus 1. Right?
Yes, sir.
And what is this? These are the, here is F. This what? Yes, correct. So this is what? This is our. So this is actually converted just, in this matrix system of linear equation form. Now we are applying, or we are using this to, try to use. So here we are actually, now this matrix will try to form the, or try to convert in the diagonal form. We'll
Yes,
try
sir. Now the rest part is understandable, sir. Okay. Thank you, sir.
Okay. Okay.
Excuse me, sir.
Yes.
Sir, you were explaining if there are two free variables, you put 1, 0 and 0, 1.
Here.
So in the example where you were showing about if there are two free variables.
Okay, yes. If two free variables are there, then vectors, eigenvectors will get by substituting one is as 0, one free variable as 0, and another is 1. And the next step, the same, that once we substituted 0 there, we'll now assume that is 1, and next one is 0. By this we will get two independent eigenvectors. Like this.
So what we will put if there are more than two free variables? Suppose
no,
3,
now
4.
we substitute. Okay, so you are saying, let's say this one. Okay, so let's say last time I got z is equal to 0 and x and y free, correct? You have, if you remember this.
Yes, sir.
In one example, I got z is equal to 0 and x, y as anything. So that means I will substitute x is equal to 0, y is equal to 1. By this way, I will get 0, 1, 0, 1 eigenvector. And now next step is, let's say x is equal to 1, y is equal to 0. By this way, I will get another eigenvector 1, 0, 0. Now you are saying what? What is the next step you are saying?
So what if there are more than two free variables? If there are x, y, z or x, y, z, w free variables?
Okay, if you have more than this, so let's say z is equal to 0 and x, y, z, x, y, w is going to be free. So that means your matrix A is of 4 cross 4. Your matrix is of A cross 4. Sorry, 4 cross 4.
Yes, sir.
Okay. So our matrix is 4 cross 4. In that case, now let's calculate the eigenvectors. So eigenvectors is going to be, in that case, let's say x is equal to 0. Now here is the combination will be made. Okay, now combination, one is y is equal to 1 and z is equal to 1. Sorry, w is equal to 1. In that case, eigenvector is going to be 0, 1 and 0, 1. W is going to be in the last. Okay, now one thing is, this is done. Okay, now next is x is equal to 0, but y is equal to 1. Okay, w is equal to 0 if we assume. Then we'll get here.
Sir, 8 possible.
So by this we will get the combinations.
So we have to take the 8 different methods. I mean, every time we have to change the 0 and 1 positions.
Yes. So just a second. So
Sir, I think no, sir, because alternatively we put a value 1. All the variables are 0. For first time x is equal to 1. For the next time y is equal to 1, and the third one w is equal to 1, and the rest of all are 0, sir.
Yes. If x, like I'm assuming x is equal to 0, rest all will be 1.
Yes,
And
sir.
the next step, now I'm assuming y is equal to 0 and rest is going to be 1. Yes. Yeah, that's the, yeah, correct. Yeah, I also started thinking how it could be. Yes.
So that
Yes.
means they are 2 to the power 3, 8 ways.
No. So by this way, you will get only 3, correct? Only 3. Because
Sir,
3 independent.
Y is equal to 1, all the others are 0, sir.
Sorry, here is now y is equal to, no, even here, this is I actually falling, no? X is equal to 0, rest all 1. Now y is equal to 0, rest all 1. Now what? Z
No,
is equal
sir.
to 0,
Sir,
and rest all.
we put 1, sir.
So 1 is substituting here, 1 and 1.
1
Rest all.
to only one variable, sir.
Okay, so you are saying if x is equal to 1, the rest all will be 0.
Yes, sir.
Okay, this is 1 we got.
Yes, sir. Then we find that all the like w and y are eliminated from the equation.
Okay, so and the next is x is equal to, sorry, now y is equal to 1 and rest all 0.
Yes, sir. That is
By this way another. Okay. So and the next is x z is equal to 1, rest all 0.
Yes, sir. You can confirm from your side, sir.
Yes. So by this way we'll get the eigenvector is x1 is 1, sorry, eigenvector corresponding to this. By this way we'll get here 1 0 0 0. Okay, and this is 0 1 0 0. Okay, and this is 0 0 0 1. Okay, even you know, even if you check, no, this will also work.
So sir, which are correct, sir?
So in this case, you know, because we want just eigenvector, okay, I want to form P, okay, even this would work. Even you can check, this is going to be your eigenvector. Even you want to confirm, no, if you want to confirm, just do AV is equal to whatever one time or whatever eigenvalue you are getting, just verify by this one. If you still have doubt, just verify by this one. Just multiply very quickly. We can do multiplication because every one is 1 and 0. So AV time alpha time that V. It could be easily verify also that which one is going the eigenvector. Okay.
Okay, sir.
Is this clear also? Who had asked? Is this clear
sir.
also?
Sir, and we can use alpha and lambda interchangeably.
Alpha and lambda.
I mean the notation.
In yeah, alpha is just this is my parameter. Even lambda, alpha, anything.
Okay, sir.
This is I am just using alpha. Otherwise, lambda we can use. Okay. Anyone else have doubt? Anything?
No, sir.
Okay. So that's all for today's session. Now on Saturday, Solvita should be. Okay. Probably Mayur will take. Mayur sir. Okay. Thanks all. Thanks to all of you.
Thank you, sir.
Good night, sir.
Thanks everyone.
Thank you, sir.
Thank you, sir.
Thanks everyone.